When we look at the landscape of our planet, we definitely need sunlight to see these landscapes. Sunlight is only one of the necessities for life on our planet. In general, the sun's rays have a huge impact on our planet, and these effects are innumerable. If we consider only the effect of photons of light coming from the sun on our planet, without it, the probability of life on our planet is zero. At this point, if we look at the size of the heat of the photons of light coming from the sun falling on the surface of our planet, the surface of our planet receives a temperature equal to 173,000 terawatts every second. This is 6 times more than the annual electric energy of our planet, which is currently produced by mankind. But no matter how much it seems, the heat coming from the sun to the surface of our planet is less than 1/1000th of the heat coming from the sun. If we consider that 1/1000th of the sun's heat reaches our planet, we know that the sun produces 173 trillion terawatts of energy in 1 second. Currently, at least 30,000 terawatts of electricity are produced by mankind in 1 year. If we compare the two, at today's electricity consumption, the total heat emitted from the sun in 1 second can supply our planet with electricity for 6 billion years. Solar energy reaches our planet mainly in the form of light photons. The origin of these photons goes back to the thermonuclear reaction in the solar core. In the process of fusion in the solar core, a large number of gamma photons are released and they go out through the radiation layer of the sun. But during the passage through the radiation zone, each gamma photon turns into millions of photons of light. The release of energy from the solar core is a very complex process. Photons released during fusion in the solar core must pass through the radiation zone. Although photons travel at speeds of 300,000 kilometers per second, it takes an average of 170,000 to 1 million years for photons to pass through a radiation layer 300,000 kilometers thick. The reason for this is the high density of the radiation layer. The density of the radiation zone decreases with distance from the center of the sun. In other words, the density in the border region of the radiation zone with the core is 20 grams per cubic centimeter. And in the outer part of the radiation zone, the density is 0.2 grams per cubic centimeter. In accordance with the situation, the speed of photons in the high-density part of the radiation zone, that is, near the center of the sun, requires a longer time for photons to escape. And in the outer part of the radiation zone, where the density decreases, it took less time for photons to escape. As a result of fusion in the solar core, in addition to gamma photons, neutrinos are released in large quantities, but unlike photons, neutrinos rarely interact with matter. Therefore, almost all neutrinos can escape from the sun immediately. Photons produced as a result of fusion in the solar core pass through the radiation layer in the form of thermal radiation. In the process of thermal radiation, photons are forced to jump from atom to atom. The temperature of the sun's radiation zone is relatively colder than the temperature in the core, so some atoms in the radiation zone may remain intact. These intact atoms can absorb energy, store it for a while, and then release that energy as new radiation. This process is almost identical to the operation of a laser device. After passing through the radiation layer, photons enter the convective zone, and they can leave this layer much faster than the radiation layer. Because the density of the convective layer is much less than the density of the radiation zone, the density in the border area of the convective zone with the radiation zone is about 0.1 grams per cubic centimeter. And the density in the outer part of the convective layer is 1/10,000th of the air density at the sea level of our planet. In addition to photons, the sun emits many other rays. One of them is ultraviolet rays, and these ultraviolet rays are emitted not only by the sun, but also by other very hot bodies. The sun emits ultraviolet radiation at all wavelengths, including extreme ultraviolet radiation. In general, UV light has a shorter wavelength than visible light. The sun is the source of the full spectrum of ultraviolet radiation, usually divided into UVA, UVB, and UVC. These are the most commonly used classifications in the earth sciences. UVC rays are harmful and are almost completely absorbed by our atmosphere. UVB rays are the harmful rays that cause sunburn. Exposure to UVB rays increases the risk of damaging DNA and other cells in living organisms. Fortunately, about 95% of UVB rays are absorbed by ozone in the Earth's atmosphere. The UV, a group of ultraviolet rays emitted from the sun, is considered the type that reaches the surface of our planet the most, and it can even penetrate under the human skin. UV rays are invisible to the human eye, but some reports suggest that bees can see UV rays. Thanks to this ability, bees find plant nectar very easily. The magnetic field and atmosphere of our planet do not transmit all the rays coming from the sun and other space bodies. So the rays coming from the sun can only be analyzed by means of equipment on satellites located outside the Earth's atmosphere and magnetic field. According to the conclusions of this analysis, the approximate index of rays coming from the sun consists of 50% infrared rays, 40% visible light rays, and 10% ultraviolet rays. Of course, these three types of rays are not all rays coming from the sun. There are many more rays, one of which is X-rays. X-rays, ultraviolet and gamma rays, are intermediate light. X-rays have much higher energy and shorter wavelengths than UV rays. Even some X-rays have a wavelength no longer than a single atom of most elements. But these X-rays come mainly from the solar corona, that is, from the upper layer of the solar atmosphere, and not from the surface of the sun, like ultraviolet rays and photons. Only very hot gases can emit X-rays, and the corona has enough heat and conditions to do so. X-rays coming from the sun are blocked by our planet's atmosphere. X-rays from the sun's atmosphere are not all X-rays from solar radiation. An example of this is auroras. High-energy particles from solar storms can be swept up by the planet's magnetosphere and cause geomagnetic storms, which sometimes led to auroras. Energetic charged particles from the sun that cause the aurora also energize electrons in the Earth's magnetosphere. These electrons travel through the Earth's magnetic field and eventually hit the Earth's ionosphere, producing X-rays. These X-rays are not dangerous to humans because they are absorbed by the lower parts of the Earth's atmosphere. No matter how much dangerous rays the sun emits, the planet's atmosphere and magnetic field perfectly filter them and ultimately pass the part of the sun that is necessary and safe for life on our planet.